Okay, but those ones that did, okay, does everybody have that one on the calculator, or some of you are already to the second one? If you're already on to the second one, just kind of watch because you've already done this one. But were you guys surprised when you hit graph on the calculator to begin with? Yeah. Right? It usually surprises students because they're like, what? Right? I put in that. Yesterday it looked really funky, but you put it in today and it looks like a straight line. Okay. Did you guys figure out why all of a sudden this one turned into a straight line? What did you guys notice, or what did you figure out? Did anybody figure out why? So that's what normally we would say, yes? But do we see that it approaches it? Right? With the naked eye, we can't see that it approaches it right now. But do we see that it does approach where x equals 3? But it's not, doesn't look like we normally see it as, because normally it like all of a sudden approaches it and then all of a sudden curves. Okay? This one does not do that. But if you go to the table of values, what do you see at 3? You do see that it's narrow. So it does approach 3 and doesn't touch it. Okay? But it's no longer called a vertical asymptote. Because, if you guys didn't know, if you didn't make this connection, this is now called a point of discontinuity because watch what happens when I factor the top. Right? And then I'll go through the definition at the top there, but I want you guys to see something. Right? Because normally as soon as you see a degree 2, we are kind of programmed by now to think, oh, that factors. Did anybody think about the top being a degree 2? Anybody? No? Right? If you didn't, watch what happens. Degree 2, we should be programmed. Factor, factor, factor. Remember the rational expressions, equations stuff you guys did in 20-1 or 30-2? The whole chapter was about factoring. These are rational functions, right? So same idea. If you see a degree 2, right, there is a chance it's factorable. And then when we factor this one, watch what happens. Two things that are multiplied to give me x squared are x and x. Two things that multiply to give me 6 are. So 6 and 1 normally would work, but I need it to be a positive 6 when I multiply them. So if I use 6 and 1, it would have to be a negative 6 and a positive 1. So that's why I can't use 6 and 1, but I can use 3 and 2. Because 3 times 2 is 6. I need a negative 5, so they both need to be negative. Because see how the inside gives me a minus 3x, the outside gives me a minus 2x. That gives me the middle that I need. And then negative 3 times negative 2 does give me the positive 6. Because remember, factoring is all about if you multiply it back all out, do you have what you started with? Yeah, so all the signs have to fix each other or match each other. So this now is all over x minus 3. Back to our rational functions and equations brain, right, from our last course. What can we do with those x minus 3's? Right, that's why all of a sudden what's left? X minus 2 is just a linear line. That's why on the calculator you see with your eye a linear line, but is there a restriction on that linear line? Yes, so you can't just say the equation is y equals x minus 2. Is there a restriction on that? Yes, it's where x cannot equal 3. Because remember, every single question you guys do in mathematics, you always refer back to your original. Even though many, many things can simplify, you always have to state your restrictions. Awesome, thanks. From your original equation. So, when you have a factor divide out from top to bottom, it's no longer a vertical asymptote. It's still a point the graph approaches, but this is called a hole in the graph. Right? So there's a hole at 3, but is it ordered pairs everywhere else? Yes. So you'll be able to recognize it because is it very clear you have factors that are the same? As soon as you divide out a factor from top to bottom, it's still a restriction, but it's no longer vertical. It's not called a vertical asymptote. It's called a point of discontinuity. So again, a point of discontinuity, a point described by an ordered pair at which the graph of a function is not continuous, right? So does that make sense, guys? It's not continuous at that point. So if you're pictured, because if you zoomed in, because right now when I look at this, whoops, can you see that it broke at 3? No, you can't, okay? I think if you zoom in far enough, you see the tiny little break, but you'd have to really zoom into there. But can you see it in your table of values? You definitely can see it in your table of values. But like I said, how you graph it, you don't do a vertical line anymore, right? If it's a point of discontinuity. So if it divides itself out, you now put it on the graph as a open circle, right? So when you graph it here, right? So do we need the output to know where it goes? Because you guys agree that there's lots of spots at 3, right? So it's somewhere on this invisible line, which we call yesterday a vertical asymptote. But like I said, this is now a point that it approaches, not a whole asymptote. Okay? So we need to know where that point is. And sometimes students are like, oh, well, I'm going to go to my table of values. Can you guys see where it's going to be there? Yeah, but do you think it's always going to be nicely there? No. So how you find your point of discontinuity without using your table of values is that you just use your simplified equation. Because do you guys agree that we crossed the x minus 3's out and we got an x minus 2? So to find your output of your point of discontinuity, all you do is use your simplified equation and put x into it. Does it make sense why I can't use my original? Because if I try to put my x value into my original, the calculator is going to kick me out, right? Because it's a 0 on the bottom. So, point of discontinuity. Right, so we are going to find f at 3. And we're going to put it into our simplified equation, which is x minus 2. So I'm going to go, so use simplified equation. So 3, well, actually I'll write my original down, just so you know where I'm getting all this from. Do you guys remember notation? Does f of x just mean y? Right? And you're probably like, why use f of x? Just because I'm using that notation to show you what I'm substituting in. So f of x equals x minus 2. So to find my output, I'm finding f at 3. So then 3 minus 2 is 1. So that notation right there, guys, you'll see a lot of that, especially in chapter 10. Right? This notation just means x equals 3 when y equals 1. So we know that that point doesn't exist. Okay? So that's my point of discontinuity. So my point of discontinuity is 3 comma 1. So that's where your open circle goes. Are we used to open circles? Remember all the inequalities? I don't, never mind. You don't remember grade 9. Right, but we did use open circles on number lines before. So, bye-bye, vertical asymptote. Hello, point of discontinuity. So we go to find 3, we go up to 1, and guess what goes there? A little circle. That is open. Because is every single ordered pair other than that one closed circles? Yeah, because all the other ordered pairs exist. Right, so then just pick a few, pick some more to get your line. And remember, they can come all off your calculator. Right, so from here, right, 1, -1, just pick a few, 5, 3, right, and then nope, because it's no longer a vertical asymptote. Do you think you're going to have some graphs that will have a vertical asymptote and a point of discontinuity? Yeah. Because if we have a quadratic on top, right, and a quadratic on the bottom. Could one of them divide out and one stay? Yeah. Or we could have a quadratic on top. Well, no, we'd have to have a quadratic on the bottom to get a vertical asymptote and a point of discontinuity, right? Because one would divide out. We won't get 2 points of discontinuity because you aren't going to have rational functions that are higher than a degree 2. Because if we had 2 points of discontinuity, would everything simplify to a 1 or a 3 or a constant? Yes. So we will get graphs that have, like I said, both. So the one that divides out is always your point of discontinuity, right? The one that stays, that's your vertical asymptote. And here, nothing stayed. So that's why everything that x minus 3's divide out to a 1, nothing's left on the bottom, okay? So therefore, only a point of discontinuity. So then let's go ahead and do our domain and range. So our domain is still my restrictions on x, so please make sure, guys, your restrictions always come from your original one, okay? So my original one was x could not equal 3. So that's my domain. So x such that x cannot equal 3, just like you would have done if before I introduced you guys to point of discontinuity, right? Coming into this, you should have thought that was a vertical asymptote because you wouldn't have known any different, okay? But now, because yesterday, did you guys notice? Nothing divided out, right? Everything didn't divide out. They were built that way purposely. So now you see that make sure if it is a degree 2 on top, right, you do factor to see if there is a point of discontinuity in the question. And then my range, do I have a restriction on y? Yeah, is the 1, right? Because I can't put 3 in, therefore I can't get a 1 out. Right? So your point of discontinuity, that point is always restrictions on x and y. Okay, so even if I don't ask for the point of discontinuity and I ask you to graph it, if I ask for range, you have to do the output of your point of discontinuity. That's always part of your why not. Right, so points of discontinuity inputs, right, and vertical asymptotes are always domain restrictions. Horizontal asymptotes and outputs of point of discontinuity are always range restrictions. So my range restriction would be my y of my point of discontinuity, because there's a hole there, right? So I can never get a 1 as my output. So y cannot equal 1. And I didn't talk about this, but I should. Okay. If I would have looked at the beginning and just went through my rules, would you guys agree that there is no horizontal asymptote because it's bigger on the top? Okay. So there isn't a horizontal asymptote, but there is a point of discontinuity, right? Which still gives me an x and y restriction. Right. So you guys go ahead. If you're already done this one, let me catch up. You guys can keep going, but like I said, I'll do this one behind you. But with this one, like I said, totally use your calculator for. But I'll kind of pop in when I'm done just to kind of bring you back to make sure you got what I needed you to get from it. So one thing as you guys are writing these, do you think I need to have that statement beside your simplified equation or simplified function? You do. If you just say f of x equals x plus 3, you can't get full marks Because is that a true statement? It's not. You need to put your domain restriction on your simplified equation. Because if you didn't, then you're saying everything exists for x, right? Where we know it doesn't. So you do need this piece. Please do not forget it. That piece is part of the work. Is everybody good with getting our point of discontinuity output? Right? It's not hard. It's just sometimes students forget. Okay. So please, 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 your POD, right? Your pod, right? Is that open circle? It always comes from your restriction on x that you normally get, which, like I said, yesterday was a vertical asymptote, but today it divides out, right? So if it divides out, it's no longer called a vertical asymptote. It's called a hole in the graph, which is called a point of discontinuity, which now is you have to represent using an ordered pair. So you do need the output of that, which use your simplified equation, put your input of your restriction on x in, 1 plus 3, 4. Okay. So any questions, guys, with any of that? So far, so good? Okay, so just keep going. So what I want you guys to do with these ones, okay, is, again, before you start, right, is I would look at this before you touch your calculator. I'd want you to know that, is it bigger on top? I'm just going to do this one first. Okay, so with this one, go through what possibly could be either a vertical asymptote or a point of discontinuity. So something like that. Do we agree it's the degrees bigger on top? So therefore we know for sure there is no horizontal asymptote. Okay? So to decide if there's a vertical asymptote, I do have to factor it to see if my restriction cancels out. So watch what I mean by that. So y equals, on top, the only thing I can do is take out a, so remember there's no constant, so I only can take a GCF out. So then I'm going to take out an x, and I'm going to be left with an x minus 2. On the bottom, what can I take out? Negative 2. So if I take out a negative 2, I'm left with, I'm going to put the x first. So negative 2 divided by negative 2 is going to be a x, and then 4 divided by negative 2 is a minus 2. Are you okay that I flipped those two things? All right, so I'm taking out a negative 2, Negative 2 divided by negative 2 is an x. I put that first. 4 divided by negative 2, right, is negative 2. And again, if I multiply it back in, right, I have my original. Right, so this one does not have a vertical asymptote. It's going to have a point of discontinuity. So you can't see until you factor it. Okay? Because if they didn't end up being the same, then you would have had a point of or you would have had a vertical asymptote. So this one, this divides out. So then you're left with y equals negative x over 2, where x cannot equal 2. So this one's going to have a point of discontinuity. And that point will be at 2, comma, negative what? Negative 2 divided by 2 equals negative 1. So there's my point of discontinuity. And then my second one. So this one, thank you. See how we're going to run into a problem with this one? So this one, if I took the negative 2 out, same as the bottom, then I'm left with an x minus 2. Thank you. Does this one have a point of discontinuity or a vertical asymptote? This one has a vertical asymptote. Right, because this one doesn't divide out. So this one, still no horizontal though, do you guys agree? Because it's still bigger on top, so that didn't change. So this one has a vertical asymptote. So if it doesn't divide out, it stays a vertical asymptote. So this one's going to have a vertical asymptote at x equals 2. So from there, we can now grab our calculator, but let's do one at a time. So what I would do is, if I wanted to do f of x first, right, I would have went, okay, I'm going to plot my POD. So 2, negative 1. And then I technically wouldn't grab the calculator, because do you guys remember how to graph a linear line? Does anybody remember how to graph this without the calculator? I would just go down 1 over 2, down 1 over 2. But if you're like, no, I don't want to, use your calculator. Okay. I'm putting in, because my POD is at 2. Right? Because it's an x minus 2, so, right, x can't equal 2, so I put 2 back in. And it's always back into your simplified. Is that all right? Did I explain that good? Ooh, ah. So then do one of the graphs, finish that one, and then the second one you would pencil in your vertical asymptote and then use your calculator to find points around the vertical asymptote. So this is where it is nice, because I'm making you do 2 graphs on one to have a different color, not to get them confused. Sorry, my POD disappeared, so I'm going to put that back on. That was my f of x. So again, 2 completely different graphs. So my orange graph is all by itself. It's my f function. And then now I'm doing my g1. So it doesn't have a point of discontinuity. It has a vertical asymptote. That one, I definitely would use my calculator to get other ordered pairs. And please make sure, guys, if you are using your calculator to graph f of x, which is fine, what should you put into your calculator? You should still put in your original, right? Don't type in negative x over 2, even though it'll still give you the same ordered pairs, right? Should you always put in your original? Because then you could at least see in your table of values that that error occurs, right? So always originals when you're graphing is a good habit to have. Right, so this graph, the second one, guys, does it look kind of funky? So this is the green one is the g of x graph. And for those ones, because I know there's quite a few in grade 11, right, if you take calculus, do you guys see that this graph actually approaches a line? It's an invisible line. That's where your slant asymptote is. Right, and you'll calculate that slant asymptote in calculus, which is literally just synthetic division or long division. But you guys just have to know that there is a vertical asymptote, no horizontal asymptote. And that one didn't ask for anything else. So one has a POD, one has a vertical asymptote. Neither of them have horizontal asymptotes. Okay. So that's where I'm going to stop. So what I want you guys to do, here's a good example of what I was talking about. Not that you had to know what this looked like, but do you guys see that one? Does that approach a horizontal asymptote on the other side? Yes. So that one is an example of it will have a horizontal asymptote. It does not have a vertical asymptote. Do I expect you to be able to write that equation? No, absolutely not. You have no idea what it is. Okay. But what I do expect you to do is, through logic, should you be able to match these from what you guys do know, which is what you know with asymptotes? Yes. So I want you to try to match each graph without touching your calculator, just from looking at this. Because if I asked you to guys look at this, should you know where your asymptotes are? Yes. No idea what the shape is. Okay. But none of these have the same asymptotes. So that's how you can logic your way through it. So look at each one of them, write down your asymptotes or your point of discontinuity if there is one, and match it that way, and then you can use your calculator to confirm. Okay? But again, I don't expect you to know shape at all looking at that. Just if you know your asymptotes, logically you should be able to fit which graph should go with which. And then there's some diploma questions you can try, and then these are good textbook questions.